here we'll see another remarkable result about constructing functions to R. Okay, so again, let X be a normal space. Let's take that as the hypothesis for now. Blanket hypothesis. And first we have the theorem. We'll come to a lemma in a moment. Suppose suppose we have a closed set. A in X is closed, and F from A to, let's say, an interval little ab is a continuous map. Then F extends to a continuous map I'll call it F again, from X to AB, from all of X to AB. So here again we don't know much about X, it's just some arbitrary space, and we have a map on this and it maps to AB, the interval. We can extend it to a real function, and plus it has the same bounds. Okay, so from an algebraic topology point of view, the thing is that AB is a convex set. It has kind of a boring space, that's why you can do it. But from our point of view now, it's still a remarkable result, because we have no hypothesis giving you map to AB. We just get it. And not, you might guess it comes from Untitled theorem, because that's where we did it. But how would we even use Untitled theorem? So the basic idea is the following lemma, okay, which let me start by stating part of it. Let F from let's say A to R be a bounded function. Let's just say a continuous function, and I'll be explicit about the bound. Be a continuous function C greater than 0 such that for all x in A, the absolute value of f of x is less than or equal to C. So we have a function that lies between C and minus C. Okay, then we can approximate it by a function g, sort of. So then there exists g from A to R such that we'll fill up the condition. So this is a lemma of a nature where we put together various things from the statements. Okay, so let me rather look at a construction first instead of trying to state the precise conditions, which will look mysterious. So here are the axes. Maybe I'll have them gray as I did last time, so they're not too prominent. So here are the axes, and here are the bounding lines. Okay, so here's a bounding line above and below. Okay, I'll label them in a moment, but first we'll put two additional bounding lines, 1/3 of the way up and 1/3 of the way down. So here are two additional bounding lines. Here's 1/3 of the way up and 1/3 of the way down. Okay, and where was I? Yeah, so let's label them a little bit. So here, there. So this is C and this is minus C. All these are just lines on the y-axis. We'll take this as C by 3 and we take minus C by 3. And we have our original function between these two lines. So what we'll do is we'll look at different parts of the function. So some parts are in the middle, some parts are high, and some parts are low. Now here I've drawn it as if it was a function from R to R. But we have no such control, so we can't partition along the x-axis, but the y-axis is R, so we can partition along the y-axis. And what we'll do is we'll approximate this by a function which, let me make it orange, which wherever the black function is high is going to be orange like this. That is where it's between C by 3 and C. Where it's between minus C by 3 and minus C by 3, it will be orange like this. And in between the two, it's going to be something. We are not going to control it. We're going to use Urysohn's lemma to construct it outside, meaning outside the region where it's here and here, but even where it's not defined at all. So we'll use Urysohn's lemma to extend it outside these special regions, the ones where it's high and the ones where it's low. So that will give us the function in general. So what do we know about the function? First of all, we'll know the function itself is going to be between c by 3 and minus c by 3. So let's record that such that mod g of x is less than or equal to c by 3 for all x in x, all of it. And secondly, because of the way we control it, above this region, the function will be c by 3, the g will be c by 3, and f is between c by 3 and c. So the difference between them is at most 2c by 3. Same at the lower end in absolute value. And in between, both f and g are between c by 3 and minus c by 3. So in all cases, mod of f of x minus g of x is less than or equal to 2c by 3. For all x, I should only say in A, because outside A, g is not, f is not even defined. Okay. So the proof is almost sketched here. We'll define the sets. A has already been defined, so let me call them C1 and C plus and C minus or something like that. Let C plus equals F inverse of so A is closed, so closed sets and closed sets are closed sets. So F inverse of, if I took minus C by 3 C and C, plus C by 3 C and C minus, C is already used, so bad choice of notation. Let's call them K plus and K minus, K and L or something like that, the upper set and the lower set. Let K be this guy. L equals F inverse of, we go from minus C to minus C by 3. L is this. And where was I? So these are the sets, so which K and L are closed. Okay, so define, let's say H. So we'll get H which goes between 0 and 1 by Urysohn. There exists H mapping x to 0, 1 such that on L, which is the lower part, H restricted to L is going to be equal to 0 and H restricted to K is 1. And you let G be the scaled version. G is going to be, when H is 0, it's going to be minus C by 3. So minus C by 3 plus, when H is 1, it has to hop all the way. So 2 by 3 times H. Okay. So the first claim on the bound is, you see G is between minus 3, 2 by 3 and so I'm not going to write out the cases, but the first bound is clear because G is between minus C by 3 and 2 by 3 plus, so let G of x is this for all x in x, okay, and it's between 2 by 3 times 1, so it has to be 2 by 3 C H of x. So it's, when H is 1, this is 2 by 3 C minus C by 3, so it's C by 3. So G of x is indeed minus C by 3 on L and C by 3 on K, and F on L is between minus C and C by 3, minus C by 3, and on K is between C by 3 and C. So the second claim is true on L, it's true on K, and it's true everywhere else in A, because everywhere else in A by construction F is between minus C by 3 and C by 3, and G is also between these two values. So you get twice that. So this is true in all cases. So this lets us do some approximation and extension at the same time. Okay, and now that will let us get the proof of theorem. So the idea of the proof of theorem is, first of all, we'll rescale. That will be our first step. Okay, by rescaling, assume F maps A to 0, 1. Instead of, that is the set AB is 0, 1, and we will map it inside this. Okay, so by the lemma, let's just find the first one. There exists G1 mapping now all of x, and it still maps it to 0, 1, such that G1 of x, its absolute value, is less than or equal to, well, the bound was 1 here, so it's 1/3 for all x in x, and mod of f minus G1 of x, this time on a, is less than or equal to 2/3 for all x in x. Okay, so now f minus G1 you can think of as a smaller function. You have succeeded in approximating this, and find a G2 accordingly. So inductively, there exists G1, G2, etc. such that, well, let me write the second bound first. G1 of x minus G2 of x minus Gn of x. This difference is less than or equal to 2/3 to the n, because each time we gain a factor of 3. And what about this bound? It's 1/3 of the previous one. So mod of Gn of x is less than or equal to 1/3 of the previous one, which is 2/3 to the n minus 1. Previous one, I mean the previous error here. Okay. So now once we have this, it follows that, well, I can look at some I equals 1 to n of gi converges to f uniformly. Okay, so these are all bounded, and this difference gets smaller and smaller. Okay, and gi are continuous. Oh, converges to, well, we don't know, some g uniformly, where g of x is some. So I almost said converges to f, so I corrected myself. So let's see why I had to correct myself. So this is some I equals 1 to n of Gn of x. So what we know about this series, so these are all real numbers. So we are back to fairly basic analysis. And this is Cauchy. This is Cauchy because of the bounds on Gns. Gns are decaying geometrically. Okay, so you can actually use the, what is it called, ratio test. It's decaying geometrically, a root test. So you see that this is actually convergent for all x. And gi converges to g uniformly, and also g restricted to the set A is f. So the first equation seems to suggest that gi's converge to f, which is correct, and converges uniformly, but uniformly only on A. Okay, so hence g is continuous. So we have this nice situation where we construct real functions which are rather useful out of nothing, just set theoretic hypothesis.